All right, welcome back, everyone. We got another video going on. We're continuing the same topic, intersections, array intersections, actually. In the previous video, we discussed and went through how to visualize all the steps to determine where on a plane the array intersects. And in case you forget, a plane that we were dealing with, it's kind of just an axis of some kind based on a point in a direction, and you can think of it as a quad or a cube, or not a quad that's infinite, an infinite quad as some kind of orientation, and that's a plane. Now today we're going to take it a little step further and determine when the array actually intersects a triangle. Why a triangle? Because a triangle is the simplest shape you can have when you're rendering things. And just like in every intersection that you're going to deal with, you always have to determine the plane. And, you know, a triangle is very simple, and it's easy to determine at what plane does the triangle exist in. So that's what we're going to really deal with today. And there's two algorithms for determining when an array intersects a triangle. So we're going to explore two different algorithms, not just one. For this lesson, there's about 5 file changes, most of it just bug fixes and improvements. The geometry class has returned from a couple of lessons ago. It has been kind of recoded, certain things renamed, and built as modules. You know, like I said, there's a bunch of things. You guys can check out the commit if you want to kind of go through the changes of fungi for this lesson. And I'll go show you what we're going to have at the beginning. So we're going to have a triangle. So here's our triangle in 3D space. It's not a perfect triangle. And instead of like in previous lesson where we hard code the array, we are now going to be able to just hold down the control key, click anywhere, let go, and then now we can rotate. Previously, every time I click to rotate, it would automatically shoot an array. But now there's some code on the page where it only shoots an array when you hold down control key. So now we can just click and it resets, and we can then experiment with testing when an array actually goes through a triangle or not through a triangle. All right, so let's start looking at some code and start dealing with some math. All right, so quick review. This is what the code looks like. Here's our geometry data and our geometry renderer. That's all good and dandy. On render, it's very simple. Here's our code. When we click on the mouse down, very simple, and then we call this. All right, so now we're going to start dealing with some code. So in the previous lesson, we hard-coded the position and the normal of the direction of the plane. This time around, we're going to actually figure that stuff out ourselves. So we're going to set up some simple variables. We got the plane normal and the plane position. We have a triangle, right? So up here, I'm building the triangle. We got 3 points. Any point on the triangle can be used as the plane point, the position. Anyone will do, because a triangle is a very simple shape, so all the points are, I think the term is coplanar. That means all the points exist on the exact same plane. When you're dealing with quads, 1 point or 2 points can be off, and you don't have a perfectly aligned plane on all 4 vertices. But a triangle, everything is coplanar, if I remember the term correctly. So that's easy to determine. Just pick a point. Any point will do. I picked 0 because why not? It's the first one. Now, to calculate the normal, we need to determine 2 vector lengths, right? So the way the triangle is built, this is 0.1, or it's 0.0, 0.1, 0.2, all right? So the idea is, if you want to quickly discover a normal, you need 3 points in space that are connected. So we're going to start with 0.1, and say, what is the distance between point 1 to point 0? And then what is the distance between point 1 to point 2? This creates basically kind of like an angle, right? So once you have the length vectors of these two edges, you can then do a cross product of those two vectors, and it'll give you a perfectly 90-degree perpendicular line. And that perpendicular line is your normal. So like I said, so plane position will be 0. Well, I'm not using number 1. I illustrated a different thing, but I'm using the starting point will be 0, and the length to 1 and the length to 2. So I guess I'm going in this direction. So from here, what is the length from here to here and from here to here? Because that's number 2 and that's number 1 and that's 0. So what are the lengths of these two edges? Or what's the vector length? Not an actual length, the vector length. Like what is the how much do I have to travel from point A to point B to get there on both an X, Y, Z axis? So once you have those two vector lengths, like I said, all you have to do is do a cross apply. And you make sure that you got the right direction, because if I swap these, the normal will go in a different direction. So if I click save, it should debug me the vector length, which it didn't. Oh, it only does it when I shoot a ray. So I got to shoot a ray. So there's my black line is my ray, and that is my my normal. Now it's extra long because it's not normalized. So it's still normal. It's still a direction, but it's not a normalized direction. But for the math that we're dealing with, it doesn't need to be normalized. So even though it's not a unit length, it's just a length vector. But we just need a normal to use kind of like a pivot point. So now that we discovered our plane position and our plane normal direction, we're good to go. So now, just like in the previous lesson, we got to determine where on the plane was the ray thing. So this is really just a rehash from the previous video. So what are we doing here? So one of the first things we got to do is figure out the length of our ray, and let's see, and get the length of the point on our plane to the start of the ray. So what we're doing is refresh, shoot. So here it is. So here's our ray. We're shooting it out. Here's our normal. This is the distance between the plane's point and the start of the thing, the start of the ray. So we got that length. And then we project this length with this normal to create this little vector. We got to create two projected vectors. Let's see. So we got to project this length to this normal, and then we're going to project the length of the ray to this normal. And then when you divide the two, it'll give us the exact position. And this just shows you one of the ratios is WP projection from like the last video. So now in this last piece of code, it's where we kind of compute the rest. So we get the VP, which would be the the denominator, which is the length between the start of the ray to the plane. No, this is the length, actual length of the ray to the normal. The distance from the start of the ray to the plane with the plane's normal, and then we divide and give us t. And I think in previous I called it k because that's what one tutorial equation used it as. But in all honesty, it's t. It's usually considered time. the traveling between the length, that's what t is. It's time. So most equations you will see it labeled as t, not k. So once we know the distance, the time distance the ratio, we'll then multiply that ratio to this this ray, and we'll then figure out the actual position. So we clone the ray delta, the length of that ray, we scale it by t, and then we add start, and then we use a new debug point. We're using debug point. It's a debug line like we did last time. Let me see, did I save it? Save, click on refresh. So if I shoot a ray, there's our dot. That is our point of intersection. And as you can see, it's exactly where the plane is. Perfect. So this is pretty much the rehash. And then you see at the bottom, that's our t. It's only 3% of our array. So this is really 3% of this huge array that goes on for a very long distance. And that's the point that it intersects. That's where the red dot is. All right. So now that we discovered the plane, and both algorithms that we're dealing with start off the exact same way. We got to figure out the point, figure out the normal, and figure out the plane intersection. So this is, like I said, this is a rehash of the previous lesson. So let's get rid of some lines that will get in our way. So we don't need this anymore. We don't need to know the distance from the plane. We don't need to know the delta. Like some of this stuff will get in our way. What's this? The normal. Yeah, let's keep the normal. We might need the normal to illustrate something. All right. Let's see. Where are we going? So now we're going to try algorithm 1, the first algorithm. Let's see. Don't need that right now, or actually I probably do need that right now. What I want to do is comment this part out. The second part is the same thing but as a loop, but we're going to just deal it without a loop. So the first algorithm we're going to do is called like edge checking. So let me give you a quick overview of what edge checking is. So refresh. So we got some lines going. What we're going to do is we're going to go determine an edge. So right now you can really see that this edge, if I refresh, you see it's blank. It's nice and green. If I click, you'll see it's got an outline. That's just to illustrate that, you know what? This is something we're dealing with. So what we're going to do with an edge checking is that we're going to determine the relationship, or not the, I don't want to say the relationship, where our point of intersection is compared to what this edge is. All right. So, and you're going to do a check on all the edges. So you're going to check this edge, you're going to check this edge, and you're going to check this edge in relation to this. Now, the quick, I guess, Cliff Notes thing is that, see how this edge exists and we have this line, all right? This is the length between the start and our intersection point. And this is the line of our edge that we're checking. So the idea is we're going to take this edge and that new edge that we just created, the length. So we have two lengths. Again, remember, just like how we were doing the projections, we're getting two lengths. So we got two lengths of this edge and this edge. And the idea is, you see how this creates an angle? If this angle is in a positive direction, then the triangle is, this creates like a true statement. Because what we're looking for is that we need 0 or positive or higher. If the angle, let's say if this is down here, So if you're thinking like I think there's a protractor or that half circle thing, I think it's called a protractor. If you put the protractor here, and if you have that half circle, is it a protractor? I feel stupid. You know what? Now I know what a protractor is. Damn it! I am horrible at spelling too. I forget what it's called. That angle thing. Well, whatever. I don't waste time on that. I'm pretty sure you guys know what I'm talking about. If you guys went to high school and you learned geometry, you got that half circle, and that allows you to determine the angle of things. Like, so if you drew lines, you can then see on that half circle what degrees it was. So if you have I feel like it's called a protractor. God damn it. Projector. Projector. I don't know how to say the word. That sucks. Math tools half circle. English is not my first language. This is what I'm talking about. Yeah, it is a protractor. I don't know why. Tractor. Okay. So yeah, think of it like that. So that's our edge that we're testing. And that second line that from the start of our edge point to the point of intersection, that creates an angle, right? So anything going up is great. That it's a positive. Anything going under that line is a negative. That means once you hit a negative, that means there is no intersection. That the point is actually outside the triangle, right? So, and that's really the gist of edge check, and you do it for every single one. So, like right here, right now, let me refresh it. If I shoot here, this is a positive. If I were to check this edge and use this point and point there, it's also positive. But if I check this edge, this is a negative. So when I do the final edge check, it will say negative degrees. That means it's false. So if I do it here, that's a positive. Over here, it's also a positive. And then here, it'll also be a positive. So that means it's inside. Perfect. That's what edge checking is all about. And here's like pretty much the equation. You get each edge, the vector length of each edge. Then you get the vector length of the start of each edge with the point of intersection. And then you do like a dot product and a cross product. And if any value is greater than 0, you're good to go. And this is how it's written in C++, and this is how it's all written in JavaScript. So here's the edge, CP. So like I said, I probably don't really need to explain it because this is actually a lot cleaner looking. But it's pretty much this is all that. You got we got the edge, we got the first point, subtracting the 0 point. Then we could take the length, we take the I position, the intersection point, and subtract it from the first, and then we create a cross, and then we do a dot. And this dot value is actually what gives us we do the dot of the normal with the cross product, and then that dot would tell us degrees. If it's 0 and greater, it's a positive. If it's a 1, it's like 90 degrees. Now the thing is, when I did it this way, I was telling you this line and this line, right? That counts as degrees. In all honesty, it's not this line that's really being used. It's actually this line. This is the cross product that you're getting. So technically, you're actually seeing it this way. But you get the exact same result. So if I have at this point, and I'm just showing you the vector length between here and here, it's still in the positive region. if I shoot it this way, where you can then see where the cross product is still in the positive region. If I were to shoot it down and you see it, no matter which line you're really looking at, it's still in a negative direction. So this is the line that we're using to determine the angle between the edge and this thing. And like I said, the cross product makes this angle that is perfectly 90 degrees of the two lines that are, even though it doesn't look like it is, ideally it should be straight. It probably doesn't work that very well because it's not, these are not normalized, but we don't need to be normalized for it to be perfect. So if it was normalized, it'll probably shoot out straight across. It's because one vector length is longer than the other. That has that weird curve, but you still get that positive and negative. So if I click refresh one more time, now we're going to look at the console. So I'm going to shoot over here, and it tells you it's 19. That's a positive, right? So that means this is positive. If we go check over here, it'd be positive. But let's see if I shoot the right down here, -5. So like I said, we're just checking to see if it's 0 or greater. If it's greater than 0, then then that point of intersection is within the realm of this triangle. So now I'm going to show you and this is really the same thing, except now I have it as a loop. What the hell? Something doesn't look right. I'm surprised this didn't break. Should be that way, right? So let me copy that over here because I don't need this right now. Like I said, this is the exact same code, but it's done in a loop. So I'm checking all 3 edges, and I just call it II because it's the next. Because I got to do 0.0, 0.1, 0.1, 0.2, 0.2, 0.0. See how once you reach the last point, you got to go back to the first point. That's what this little equation does. It creates this exact pattern. So I will be 0, 1, 2, and II will be 1, 2, 0. So that's what I'm doing. Like I said, it's the same math equation, 2 vector lengths and the cross, and then giving you the dot product. So if I click refresh, hopefully I didn't break anything. Now when I click outside, you see all the lines being drawn, and you'll see positive, positive, negative. It's true. If there's at least one negative, that means that dot is not in there. Refresh, and I do it on the inside. All 3 show positive, and it's correct. It's on the inside, and you see all the vector lengths that go straight into it. That's exactly where it is. Like I said, that is the ray. That's the point of intersection, and then you have all these checks to see if it's within the positive or negative range of the edge when you do that, like an angle check. And there you go. And that is one way to check to see if there's an intersection in a triangle. Now, this algorithm is not the most efficient way for a triangle. Definitely not. It's more the slowest way because you have to do cross product, dot product, and a bunch of other mathematics. Now, what this algorithm is good for is when you're dealing with polygons. So the next equation is the algorithm I'm going to show you is more efficient for a triangle and probably even for a quads. But when you're dealing with more than 3 points, this algorithm is probably pretty good. Now, if you're dealing with like a 5-point or 6-point or a 20-point polygon, like think about like a hexagon that has 6 points. This algorithm is what you're going to use for checking of intersection. So if you're going to build like a hex grid, that's one way to check to see if you clicked on that specific hex grid. if you're going to do that check, you're probably better off with a different equation. But for the most part, if you want to do like a hex, use this edge detection. And then what you can do is just loop around that shape and just test to see if that angle is within the positive range of that edge. And that's what the algorithm is for. It's an edge testing thing. So so ideally, if you have a coplanar, that's one of the requirements. It has to be coplanar. All the points have to exist on the exact same plane. So it has to be perfectly flat. That means you can use this thing to test an infinite amount of points as long as there are in the same plane. So that is the end of that one. So the way I had it was I had this like that. Then now we're going to deal with the equation that is more geared toward triangles, like more efficient. Like it's like there's no cross products. It's really just two edges and I think 2 or 3 edges, 2 projections, and one dot product. Let me see if I can find a nice image of what we're doing with. I probably should really check these out. But like I said, I'm always do triangle intersections. Nope. No, this doesn't have an image of what we're trying to do. All right, no big deal. Like that's the whole point of this. Well, here's a polygon. You can use this, like I said, that previous equation that we're messing with. You can check every single edge, and if all of them are positive, that means you had, oh yay, look at me. I'm finally on a Google search. Yay! All right, that's funny. All right, so refresh. Everything's good. Let's go back to the code. All right, so barycentric coordinates. This is what this algorithm is called. The idea of that's what the equation called, but it's to me it feels like it's not how you're really using it. The idea is that you assign each point a number, right? Or not a number, really. Like this point will be like 1, 0, 0. This one will be 0, 1, 0, and this one will be 0, 0, 1. There's 3 points, there's 3 coordinates. And each corner gets a coordinate full 1. So the idea is that the further away from this corner you are, the further away the less that coordinate value is going to be. So if I click here, the coordinate is going to be greater at 0, the first, like let's say the x position. If I'm all the way over here, the x position is going to be 0 for that barometric coordinate because I'm at the furthest point away from that point. And same thing. So what this algorithm does is that it tries to project this point onto this edge. And then you only have to check 2 edges with this too, which is kind of neat. So you kind of project this point to this edge, and then you do the same thing to the other side. So you kind of create this like X inside a triangle. And by projecting where the mouse or where the intersection point is on those 2 planes or those 2 lines, you can tell if you're inside the triangle. So instead of checking the edges, you only need to check 2 edges and basically peel across inside. So if we're going to illustrate it, let's see. So this, you can kind of get an idea what it really looks like because I can't find an image. So we're gonna, let's say we're gonna get the 2 edges. We're gonna get 2 edges, right? A and B. Let's see. So A and B. So that this is A, and this is B, right? What I want is to make a perpendicular line from here to here, right? Perpendicular line, if I remember my definitions, is that is a line that is 90 degrees. So on this edge, I want to cut this triangle in, not necessarily in half, but I want to cut this triangle into two triangles, and I need to find a point on this line that can connect to this point to make a 90-degree angle that exists on both sides of the triangle. So that's the first step, is that I need to find that perpendicular angle. And what you can do is we're going to do projections again. So we're going to take this edge and project the length of this edge onto this edge. So this way it makes a perfect line. And the projection equation is the length, the vector length of the edge that you want to project, dot product with the vector length of the edge you want to project it onto, divided by the vector length of the projected you want it to, dot product of itself. If these two are normalized, you get a value of 1. But since we're not using normalized values, you will actually get an actual something other than 1 equals t. So this way, by doing this, we know how far in this edge we need to go to create a perpendicular line from the vertex 0. So this is, like I said, this is really just the equation. So I'm getting edge A, edge B, using the dot product of both and dividing it. And then the rest of this is really just for visualization. So if I refresh, if I shoot a ray, there it is. There's our ray. That's the point of intersection. There's our normal. And there is our perpendicular line from this point to that point. And that's the first step. So now let's see how we projected this length onto this length to get that. Now the next thing is take this line and create a new line from here to here and project this line onto this line. So we're doing the same step twice. So we're cutting this triangle in half based on this angle. And now we're going to use the new line and create another line and create that angle and project it right across. So like I said, we're going to create another perpendicular line. So ideally, it should go straight here. All right? So it's basically, like I said, it's really the exact same thing all over again, but just for two different lines now. So we get the perpendicular length is that, you know, that we're going to get its vector length from A to P. We're going to get the intersection length, which is from here to here. And then we get the dot product, we divide it, and then we finalize. Like I said, it's the same process twice. Refresh. Now if I shoot it back out again, there you go. Now, here's the thing. It's not perfectly perpendicular because there's something really funky about this equation. Now, the equation I found is, like I said, this is to determine the barycentric coordinate. So to find the barycentric coordinate, you have to subtract 1. Because like I said, the further away from this edge you get, the closer to 0 you should be. So you need that -1. But I made a note here. You don't really need to do this if you do not care about the barycentric coordinate. If I take this out to make it go in reverse, so the closer to the edge you are, or the closer to that starting point, the greater to 1 0 or 1, or whatever, either way, I forget. So if I refresh, shoot it again, now it's a perfect perpendicular line. It doesn't. Like I said, it does not matter. If you don't care about the barycentric coordinates, take away the 1 minus because there's no need for it. Like it's useless. If all you care about is determining the intersection point within the triangle is successful. So yeah, it looks like the closer you get to this edge, the closer you get to 0. Whereby if you do that -1, the closer you get this edge is 1. But that's only if you care about barycentric coordinates. So if I go back and just undo it, like I said, if you're gonna write this into a function and you only care about intersections, you can take that out and save yourself one math operation. It's like I said, it's not needed, but it is part of the equation if you care about that. Again, I would keep stressing it because this, like I said, is 2 different topics. This determines a certain type of value if you're looking for it, but at the same time, you can use this to determine if there is a collision. So let's see. So let's see if I do here, I shoot my line there. And this ray, right? See where the blue dot is here? That is this line being projected on that ray. And you got to think about this, even though there is a defining distance between here and here, the line is infinite. That's why the point shows up here. Now see the final dot value is negative 0.7. If you get a final dot product for this check, that is, let's say, well, the value has to be between 0 and 1 because we're doing this whole length. So if the value is between 0 and 1, then you're inside the triangle. So let's say if I shoot the second ray here, now the value is 0.5. It's between 0 and 1, but because it actually is inside the triangle. So the idea is that we're projecting this, our intersection point, to a line inside the triangle, which now creates a positive. So if I shoot my line outside, there's the projection that it goes there, and I get a value greater than 1. That means it's a false. That means I only need between 0 and 1. Like I said, so now the only thing left to do is that you need to do this one more time, but from another edge. So remember, like I said, we projected this edge onto this edge to create this perpendicular line. Pick another edge, either this edge or this edge. So like I say, if I take this edge, project this onto this edge or that onto this edge. So you basically kind of, let me see if I can just refresh. So this way you can create another perpendicular line that goes across the triangle. So if we go from here to here, it creates like a cross. And when you project this point, like this point onto those two new lines, if one of those lines does not exist between 0 and 1, then it did not intersect the triangle. So it's kind of basically what you're doing is kind of creating this like little range, like this little X marks the spot type of range to determine if it shows up. It's kind of like a net trying to catch that dot. So like since there, I catch the dot, I catch the dot, I catch the dot. I did not catch the dot. I did not catch the dot, did not catch the dot, did not. It is catched. As you see, sometimes you catch and sometimes you don't. So if you have the second intersection point or the second perpendicular line in there, if you compare the two, you can then determine if it really is a collision. And that is the gist of this algorithm. Like I said, this algorithm is a lot simpler. It's really just a lot of addition and subtraction. Like I said, there's let's see, there's two subtractions, 2 dot products, 1 division to determine 1 perpendicular line of intersection. You do that a second time to find the projection of the intersection of the between another edge, and that's it. So if you do the first one and it's not between 0 and 1, you can automatically say false. It did not pass. That means you need to do this again a second time for another edge, and that's how you do a triangle. This probably will work also for a quad. I haven't read too much about how to do quads or squares yet. There's really not much information. Sometimes they just say, just turn a quad into a triangle, and that's good enough. I'm also, since this way of doing it where you kind of create that perpendicular line, I wonder if I can create a perpendicular line in the center of the triangle of a square, and then follow the same process of projecting. Projecting the intersection point on those two lines of intersection. So this way you can determine. So I was thinking you can do the same thing on a quad. Take one, just make some kind of thing across. Or maybe I don't need even to do that. Maybe take 2 points. Like if you have a quad, just check to see, just project it on an X across the X across the quad. So you know how I have a line across here and another across here. So this way you don't have to really. I guess it's the same thing, except you don't need to do a lot of dot. Probably one less, 2 less dot products or whatever. So maybe in the next video I might experiment on doing something like this myself on a quad. And then since we have a quad, I might also do like a disk. Have like a little shader that draws a circle inside a quad. So this way you can have like a circle, like a flat 2D circle intersection type of thing going on. Since we're doing quads and we need a quad to draw a circle anyway. So maybe that will be the next video. So next video, like I said, we're going to continue with more intersections. And then we're going to start moving into 3D. We're going to spheres, bounding boxes, and I want to see if I can find a way to deal with capsules, because Unity 3D uses capsules a lot, and I think also Unreal Engine uses capsules a lot as a collision box of some type. So that's what I'm kind of hoping to try to do. So that'll probably be the last thing, the last intersection, if I can find enough information about intersection, because that's more of a complicated shape compared to a box or a sphere, because that's like 2 half spheres and then kind of like a cylinder in the center. So yeah, that's really the plan for intersection. So we're gonna at least let's see, like I said, there's quads and disks. I'll probably do the next one. After that, I'll see if I could do bounding boxes. There's 2 types of bounding boxes. There's the AABB, and I forget what the other one's called, is OBB. ABB and OBB are the same thing. The only difference is AABB, I think, axis aligned bounding box. The box does not rotate at all. So it's just like a bounding box, and the character or the object that's inside this box can rotate and go anywhere. The only difference is that the bounding box center position matches up with the item inside of it. That's about it. But it does not rotate. And I think OBB is oriented bounding box. So if you rotate, let's say, your cube, or you rotate your cube, the bounding box rotates along with it. So it's a more accurate intersection than just a plain old axis aligned bounding box. So that'll be second video after the next one. Then maybe do spheres, or maybe I should do spheres first, because apparently when you deal with intersections, you're supposed to do spheres first. But I didn't bother with doing that, so I went straight to planes and then triangles. So maybe I'll do spheres after. That'll be maybe the first 3-dimensional shape. We'll do spheres, then we do bounding boxes, and then we'll do capsules. So so we got 3 more videos worth of intersections to deal with, and then planning to go back to 3D animating skeletons. So hope you're enjoying this video. I got apparently a lot of good feedback, or popularity. So it seems like you guys really like intersections, and I guess you guys really like the idea that I'm visualizing each step, so you can kind of play with the math a little bit and see how everything works. I hope I'm doing a good job explaining to you how this stuff is working, and it's kind of fun that you can kind of click around and kind of see where everything kind of intersects. So it's kind of useful. So I hope you guys are learning. Hope I'm making it easier for you guys to do this. I think once you get to bounding boxes, we can then start selecting things on the screen, and we already know how to do like access finding. So this way, we could just, like if I point here, like if I do an axis just on the ground, I can actually find exactly where I intersect the ground, so we can start moving things around. So I think in 3 videos we can start. I might go back and forth between the floor plan app. I don't know. Too much planning. It's probably boring you the hell out of you, making this video longer than it should be. So yeah, hope you guys are having fun. Again, hope you're enjoying learning about intersections, because this is a very fun topic. I remember 9 months ago when I started this, I tried to understand collisions and intersections. I couldn't, for the love of life, could not figure this out. I could not understand this. 9 months down the line, I actually understand some of this. It makes more sense now. I can actually probably take what I've learned about triangles and now apply it to a cube and see if it works. So cross products, dot products, they're a lot more fun now that I understand how to use them. And I'm starting to get pretty good at vector math. Hopefully you guys are too, following along with me. And like and subscribe. If you have any questions, ask away. And see you guys at the next intersection lesson. See ya.